The, the next paper has the title, The Pull-in Range and Counterexample to the Eigen Conjecture for Fourth Order Type 2 Analog PLL. And I understand it's going to be presented by Mikhail Lobachev. You have 20 minutes, and your time starts now. Thank you.
Dear colleagues, my name is Mikhail Lobachev. I am from St. Petersburg State University. First of all, I'd like to thank the organizers who are arranging the conference in such difficult time considering the last news from South Africa, and also sending everybody wishes of good health. Now let me introduce our presentation, the pull-in range and a counterexample to the Eigen conjecture for the fourth order type 2 analog PLL, written along with Nikolai Kuznetsov, Marat Yuldashev, Renat Yuldashev, Vladimir Kuznetsov, Geza Kolumbian, and Leonid Chechurin. After a short explanation of operation principles of phase-loop loops, we will present a mathematical model and state the problem. Then we will introduce the Eigen's conjecture and proceed to the fourth order PLL discussion. Finally, main results will be formulated and some numerical simulations will be shown. The main purpose of PLL is to synchronize two oscillators. This idea takes root from Gürgen's work on synchronization of two pendulums. Consider two pendulums connected by a platform. If you hit one of the pendulums, it starts oscillating, and after some time the second pendulum starts oscillating too, and synchronizes to the first pendulum. This is an example of a mutual synchronization. In electrical circuits we need to synchronize frequency of the voltage-controlled oscillator, that is VCO, to the reference signal. This is called a master-slave synchronization. Instead of a platform, in PLL we have two blocks, phase detector and loop filter, which allow to synchronize signals. However, if PLL is constructed in a wrong way, the signals may never synchronize, so a correct choice of the circuit's parameters is a very important step in PLL design. Consider the analog PLL baseband model, which is described by a n+1 order nonlinear system of ODE. Here x of t is a filter state, theta e is a difference between input and VCO phases, A is a n by n matrix, B and C are vectors, D is a number. Loop filter has transfer function f of s, k VCO is a VCO gain, and omega e3 is a frequency error, the difference between the reference frequency, which assumed to be constant, and the VCO free running frequency. Note that the system is a 2p periodic by theta e. The model's parameters can be derived by the circuit's parameters, which we denote by lower c, and input parameter omega e3. Let the input parameter omega e3 is equal to 0. Define a set d-hold-in in the parameter space as circuit's parameters such that the PLL model has asymptotically stable equilibria. For each element of the set d-hold-in, the largest interval of frequency errors, such that the PLL model has asymptotically stable equilibria, is called a Holden range. In a similar way, define a set d-pull-in from d-hold-in as the circuit's parameters such that the PLL model is globally stable, that is, each trajectory of the system tends to an equilibrium. For each element of d-pull-in, the largest interval of frequency errors such that the PLL model is globally stable is called a pull-in range. Our goal is to determine domains of parameters d-hold-in and d-pull-in, and to estimate the hold-in and pull-in ranges. Note the set d-hold-in and the corresponding hold-in range can be determined precisely by the Rausz-Gurwitz criterion. However, the determination of global stability domain and the pull-in range estimation demand nonlinear analysis in the cylindrical phase space, which is a challenging task. First of all, it's worth to note that the well-known Borbashин-Krasovsky theorem and LaSalle invariance principle cannot be directly used for global analysis of systems in the cylindrical phase space. Such systems have an infinite number of equilibria, and Lyapunov functions of quadratic path plus integral nonlinearity form, which is frequently used for global analysis of such systems, are not readily unbounded. To overcome these difficulties, it's possible to use the theorem which extends the Borbashin-Krasovsky theorem for the cylindrical phase space. Thus, for global stability analysis of phase synchronization systems, it is sufficiently to choose a periodic Lyapunov function such that it is readily unbounded by non-periodic variables, such that it doesn't increase along the trajectories, and which is constant for stationary solutions. Unfortunately, this result on the global stability in the cylindrical phase space is almost unknown in the PLL literature. As a result, works where not suitable theorems are used for global analysis appear, and some methods popular in absolute stability theory, such as Popov stability criteria and circle criteria, are used for obtaining only local stability results in PLL systems. As a simple example, consider the following second-order PLL model. Here there are three circuits parameters, tau1, tau2, and KVCO. Using the Raus-Guritz criterion, it's easy to prove that the system has two kinds of equilibria. First of them are asymptotically stable, and the others are unstable. Consider the following smooth 2p periodic Lyapunov function. Its derivative along the trajectories of the system is equal to 0 only in equilibrium points, otherwise it is negative. Obviously, it is radially unbounded by variable x, thus it satisfies the conditions of global stability theorem, and hence the system is globally stable for all values of the circuits parameters and for all values of the input parameter omega e3. The considered model is a type 2 control system, that is the open loop transfer function of a linearized system has exactly two zero poles. An American engineer, William Egan, conjectured in his books that the type 2 phase-locked loops have infinite Pullen range. Egan's statement posed a challenging engineering problem to determine a class of type 2 PLAs for which an infinite Holden range implies an infinite Pullen range. In other words, are d Holden and d pull-in equal to each other for type 2 PLLs. The first counterexample to the Egan conjecture was introduced for a third-order type 2 PLL in the article presented below. In this work, we consider the fourth-order type 2 PLL having the following loop filter transfer function. This loop filter transfer function is the third-order one. It has two negative zeros, two negative poles, and one pole at the origin. N+1 PLL model turns into a fourth-order one, and open loop transfer function of linearized model has two poles at the origin, making the system type 2-1. Pole at the origin allows one to make a linear change of variables in the system such that a new system doesn't depend on the frequency arrow directly. Thus, stability properties of system doesn't depend on omega e3 and hence, if the circuit's parameter are such that the system is stable for zero frequency arrow, that it is stable also for all values of omega e3. That is, if d Holden is not empty, then the Holden range of type 2 PLL model is infinite. Also, if d pull-in is not empty, the pull-in range is infinite. Finally, in a type 2 PLL model, we need actually to estimate sets d Holden and d pull-in. To perform local stability analysis, equilibria of the system were determined. Then the stability of this equilibria was evaluated by Raus-Guritz criterion. The conclusion is the condition on the bottom of the slide is satisfied, then the system has infinite number of asymptotically stable equilibria and also infinite number of unstable equilibria, which alternate with the previous ones. Otherwise, any equilibrium is unstable. Now let's study global stability of the considering system. Again, we used a Lyapunov function of quadratic part plus integral of nonlinearity form for global analysis. The conclusion is, if condition 4 is satisfied, then the system is globally stable and the Pullen range is infinite. Note that in contrast to the set d Holden, which was determined precisely, the set d pull-in is only estimated. There is a gap between two sets. D hold-in corresponding to stability of the linearized model and D pull-in corresponding to global stability. To analyze the behavior of the system for parameters from the gap between obtained conditions of local and global stability, let's fix parameters from this gap and make a computer simulation. Here green and red dots are asymptotically stable and unstable equilibria correspondingly. The black trajectory from the vicinity of an unstable equilibrium tends to a stable limit cycle of the first kind. Hence, stable oscillations may develop in the higher order type 2 PLL in steady state, which is a clear counterexample to the Egan's conjecture. On the slide, we can see each coordinate of the trajectory from the previous slide separately. In this work, the analytical estimate of the pull-in range of the fourth order type 2 analog PLL was obtained. The present paper is a continuation of article where the Egan problem on the pull-in range was considered for PLL with the second order loop filter. Conditions for global stability of Z, third order loop, coincide with the obtained ones if we formally set tau p2 equal to 0. However, the obtained conditions of pull-in ranges infiniteness of the third and fourth order type 2 PLLs are conservative ones. Further global analysis of the higher order type 2 PLLs demands the study of hidden oscillations by application of special analytical numerical methods. References are presented on this slide. Have a nice conference and be healthy.
Thank you, Mikhail.
Yes, thank you too. Can you hear me?
All right. So now we have time for questions, contributions, and I wonder if we have anything on the chat. Otherwise, on the floor here, anybody contributing or having questions or
Can't
whatever.
see any questions in the chat.
Yeah. So there's the question. Apparently, there's a question. Can you see that? Point to it. Can you help us point to it?
Yeah, thank you, Mikhail.
Yes.
Can you hear me?
Yes, I can hear you.
Thank you for thank you for your beautiful presentation, and I like the way you use route Howitz criterion in the process of deriving your stability result. That's kind of interesting. Mine is just more of a comment and not a question. So I see that you made reference to master-slave configuration during the course of your presentation. So I think that kind of reinforces existing biases, in engineering. So I would suggest maybe in the future you revise, the use of such like master-slave, maybe something like leader-follower or something else might be better used for that kind of configuration. That's just my comment.
Okay, thank you for your comment. I believe that we took that term from some engineering book about phase lock loops. I think we can find it in book of Roland Best, which has about 6 editions. So I need to check it, but thank you. I will check your term also. Thank you.
Thank you. Thank you.
Okay. Any other contributions about slave master? Cascade control also, we hear that about slave master.
Спасибо, Michael. Very interesting. I'm checking Google. It says the temperature is minus 15. Is that correct? I just want to know, is the temperature really minus 15 in St. Petersburg today?
Yes, I think that it's about minus 15 degrees of Celsius.
I have to tell you, it's 30 degrees in South Africa. Sorry. Well, thank you again.
Thank you for your presentation. I think that, thank you very much for your presentation. I think we are ending this, and you can give me a round of applause, please.
Thank you for questions and comments.